Today, we'll dive into the world of measure theory, a cornerstone of modern mathematical analysis that focuses on assigning a size or volume to sets. This is essential for underpinning many advanced concepts in mathematics. Let's explore the key aspects. First, measure theory allows us to quantify the magnitude of sets, which extends beyond the traditional focus on shape within topology. This quantification is foundational for the fields of continuous probability and real analysis. Another crucial aspect is the principle of countable additivity. This property is what distinguishes measure theory from mere finite additivity, and it lays the groundwork for Lebesgue's measure and modern integration theory. For example, in probability theory, measure theory is instrumental in defining probabilities in continuous spaces, such as calculating the probability that a random variable falls within a specific range. Let's discuss finite additivity. A measure, denoted by mu, is considered finitely additive if for any finite union of disjoint sets A1 through AN, the measure of the union equals the sum of the measures of each individual set. In more technical terms, this is expressed as mu of the union from I equals 1 to n of AI equals the sum from I equals 1 to n of mu of AI. This property ensures consistency of the measure across finite decompositions of sets. Moving on to countable additivity, also known as sigma additivity, a measure mu is countably additive if it extends this additive property to countably infinite collections of disjoint sets. This is crucial for handling infinite sets and processes. Formally, we express this as mu of the union from I equals 1 to infinity of AI equals the sum from I equals 1 to infinity of mu of AI. This condition is a pillar in modern theories of measure, particularly evident in the Lebesgue measure. In the context of Lebesgue measure and integration, we come across several fundamental concepts. Measure itself is a systematic way to assign a number to subsets of a given space, which goes beyond simple dimensions like length, area, or volume. Sigma algebras, or collections of sets for which measures are defined, are crucial as they are closed under countable unions and complements. Measurable functions are those functions that map elements from a measure space to a target space in a way that respects the structure of the measure space. Lebesgue integration is a method of integration that generalizes the concept of integrating functions, particularly effective for functions difficult to handle with traditional Riemann integration. The dominated convergence theorem is a key resulting Lebesgue integration, allowing for the exchange of limit and integral operations under specific conditions. Let's define a sigma algebra, denoted as M on a set X. It's characterized by the following properties. The empty set is always a measurable set, indicating that the empty set belongs to M. If a set A is measurable, then so is its complement, expressed as if A belongs to M, then A complement, which is X minus A, also belongs to M. The collection M is closed under countable unions, meaning if sets A1, A2, A3, and so forth belong to M, then the union over I of AI also belongs to M. This structure, known as a measurable space, differs from topological spaces by ensuring that the complement of a measurable set is always measurable. Let's engage with an exercise to deepen our understanding of sigma algebras. The task is to show that any countable intersection of measurable sets is measurable. To approach this, consider leveraging the foundational properties of a sigma algebra, specifically its closure under countable unions and complements. These properties will guide us in demonstrating the measurability of intersections. Imagine we have a countable collection of measurable sets, denoted as A sub I, where I ranges from 1 to infinity, all within a sigma algebra M. Our goal is to prove that the intersection of these sets, the big intersection from I equals 1 to infinity of A sub I, also belongs to M. Here's how we do it. 1. Start by considering the complements of these sets, which are A sub I complement. 2. Apply the closure property under countable unions to these complements. 3. Finally, reapply the complementation property to this union to retrieve the original intersection. Let's consider the structure of algebras through examples. The smallest, sigma, algebra for any set includes just the empty set and the set itself. This is represented by M equals the set containing just the empty set and X. Contrast this with the largest sigma algebra for X, which is the power set of X, denoted as 2 raised to the power of X, encompassing all possible subsets. These examples help us appreciate the range of complexity sigma algebras can possess. Shifting our focus to topological spaces, let's discuss Borel sets, the smallest sigma algebra containing a particular collection of subsets, A, within a space X, is termed the sigma algebra generated by A. In the context of a topological space X, Borel sets are defined by the smallest sigma algebra generated by the open sets of X. This includes all open and closed, and it extends further to complex constructions that are neither open nor closed. Diving deeper into Borel sets, particularly in their number line, math R, these sets form the smallest sigma algebra containing all open intervals. This sigma algebra is denoted as mat R. An example of a Borel set is any open interval, say AB. More complex Borel sets include closed intervals like B and countable unions of such intervals. To further illustrate Borel sets in the real line math R, every open set can be described as a countable union of open intervals, thus forming a Borel set. Infinite intervals, such as A infinity, are expressed as the countable union from n equals 1 to infinity of the intervals A plus n, making them Borel sets. The complements of these sets, including both minus infinity A and A infinity, also qualify as Borel sets. Consequently, all closed intervals, which can be expressed as minus infinity B intersected with A infinity, are Borel sets. Let's explore the concept of a product measurable space. When we have two measurable spaces, let's call them X with a sigma algebra M and Y with a sigma algebra N, we can define their product measurable space as X times Y with the sigma algebra M tensor N. The algebra on the product space X times Y is generated by all sets of the form A times B, where A is a member of M and B is a member of N. The implication of this definition is quite significant. It allows for the construction and analysis of measurable sets in product spaces, extending the concept of measurability to higher dimensions and more complex structures. Moving on to measurable functions, consider two measurable spaces, X and Y again. A function from X to Y, let's denote it as f, is said to be measurable if the inverse image of every measurable set in Y is measurable in X. In formal terms, this means that if A is a set in N, then the inverse image of A under function f must belong to M. This definition is similar to that of continuous functions in topology, where a function is continuous if the preimage of every open set is open. Here, measurability plays a similar foundational role in measurable spaces. Now, consider a theorem that bridges continuity and Borel measurability. If X and Y are topological spaces, and if M and N are their sigma algebras of Borel sets, then every continuous function from X to Y is Borel measurable. To prove this, consider the families of open sets in X and Y. Since the function is continuous, the preimage of any open set in Y under this function will be an open set in X. We define a sigmas algebra, let's call it N prime, as the collection of subsets B in Y, such that the preimage of B under function f belongs to M. This collection is a sigma algebra because it satisfies all the necessary properties, and since it includes all the open sets of Y and by extensional Borel sets, we conclude that the inverse image under function f of any Borel set in Y is a Borel set in X, making f Borel measurable. For an exercise, consider proving that a function from X to the real numbers, math R, is measurable if and only if, for any real number A, the set of all X in X, where the function value is greater than A, is measurable. The hint here is to express this set as the preimage of the interval from A to infinity. The intervals of this form generate the Borel sigma algebra on math R, so proving this for all such intervals suffices to establish the measurability of the function. In solving this, first assume the function is measurable. Then, for any real number A, the interval from A to infinity is a Borel set, and by the definition of measurability, the preimage of this interval under the function, which is precisely the set of X where the function value is greater than A, must be measurable. Conversely, assume that for any A, the set of X where the function value is greater than A is measurable. Since these sets correspond to the preimages of intervals that generate the Borel sigma algebra, the preimage of any Borel set can be constructed from these, proving the function's measurability.